All right, so we're continuing with rotational inertia. We'll have a free response question to go with it. I'm going to really quickly review some stuff on inertia before we get into the free response stuff, though. So we'll need parallel axis theorem, and it's been a while. When we talk about inertial mass, so just mass, what we really mean is the ability of an object to resist linear acceleration. So we can do a rotational analog by saying that rotational inertia is the ability to resist rotational acceleration. So which would be easier to bring to speed? If you had an object like a top where all the mass is towards this axis of rotation, or if you had an object like a carousel where all the mass is further away from the center, so further away from the axis of rotation.
Which one is inertia? Which one has greater inertia?
Yeah, that's what I'm getting at. But which do you think would be easier to get to a high velocity?
High velocity is the first one.
The first one. Okay, that has all the mass close to the center. So which one would have the most inertia?
Bottom one.
The bottom one. Okay. Because once it gets moving, it's harder to stop. Cool. So the more your mass is away from the axis of rotation, the more inertia it's going to have. Okay, these are some common moments of inertia that I pulled from our textbook. So we've got a solid disc or solid hoop, and then a hollow hoop, a hollow sphere, a solid sphere, a rod, either at the center or a rod at the end. The parallel axis theorem says if we shift the axis of rotation away from the center of mass, then we can add whatever that distance is from the center of mass times our mass squared, so however much our mass is away from the center of mass. So using this, we can shift our axis of rotation away from wherever the center of mass is, and figure out what our new rotational inertia is going to be at that new axis of rotation. Okay, any questions on any of the review stuff?
Nope.
Okay, then let's go ahead and try a problem. Okay, so here I've got a spring scale and a hinge, and then off that hinge I've got a rod with a mass that's hanging off the end of the rod. There's a 30-degree angle between the length of string that's attached to the spring scale and the rod that's supported by the hinge. If I wanted to draw and label the vectors that were representing all forces acting on the rod, what do I need to draw?
So there is a weight at the right.
Okay, so what can I label that as?
MBG. B is the mass of block, maybe easy block.
Okay, see, so that's the subscript, so mass of the block
Yeah, MBG.
times gravity, okay?
It's just block. And the weight, is it called? No, rod.
Rod.
The weight rod itself.
Okay, what can I label that?
MRG.
Okay, M sub R G. Okay, mass of rod times gravity, looks good.
And there is a tension.
Okay, there is a tension. Should I start that arrow on the right side or the left side?
Start from rightmost, going to how do you say it? 30 degree going up.
Okay, going 30
It
degrees
starts
from the
from
rod.
the right, yeah, rightmost of the
Okay,
road.
and label that as
Just T.
tension. Okay, there's one more.
There is a supporting force at left. Maybe
Okay.
friction?
Okay.
I don't know how to name it.
I'm just gonna label that as H for the force on the rod by the hinge. What
Force
direction?
H?
Yeah, I'm gonna label it as H because that's the force of the hinge on the rod.
Okay.
But what direction does it go? And where does it
It starts from left and going up diagonally.
diagonally? Okay. So
Yeah.
this is H. Okay, cool. So we knew that I had to go diagonal because the supporting force is going to help lift it up, but also we've got all of this tension that's pushing us to the left. And because our object is not in motion, we have to balance that with some force moving to the right.
Yeah.
Okay, I've got more room on this slide because we haven't used any of this yet, so I'm just going to stick on this rather than moving. And we're going to go B, so I want to calculate the reading that's on the spring scale. What do you think I can use to set up how can I set up an equation that will help us solve for the reading on the spring scale?
So it should be balanced.
What needs to balance?
So torque.
Torque. Okay, torque's of what?
So tension times R is equal to inertia alpha. So tension times the length of the cord.
Okay, let's just we said we've got torques. There are 3 torques that need to balance. From our picture, what are the 3 torques that need to balance?
So horizontal, no, I mean vertical part.
Okay, we're just looking at the
So
vertical.
tension and two weight.
That's it. Okay, so I've got torques for tension and the 2 weight. So I'm going to say my torque for the tension has to equal the 2 torques of weight. Is that fair?
Yes.
Okay. Then my torque for the tension is not this entire torque, it's just the part that's moving vertically, right?
Yes, so that's T sine 30 and R, which is it given the length of?
I believe it is.
No,
I'm
not.
just going to write L for now. So TL sine 30
Mhm.
equals, okay, so that's my torque going up. So that should balance with my torques going down. So I've got 2 torques going down.
MBG.
Okay, mass of the block times GL, because that's at the end of the length.
Oh yeah, and then MRG half L.
Right. Sub R G, oops, of G times L over 2. Okay, that was good. So now we should be able to start substituting and solving for T.
Yes, sine 30 is half.
Okay, sine 30 is 1/2, and then I've got an L and an L and an L, so I can get rid of all of my L's. So this is T over 2 equals MBG plus mrg over 2, and then I'll multiply through by 2. T equals 2 mass of block times gravity plus the mass of the rod times gravity.
Yeah. Mass is 0.6, no, 0.5 is the block and 0.6 is the rod.
Okay. Okay, I'm going to stick to 10 for gravity. So this is 10, and then the mass of the rod, 2 by 10. Okay, so what should my answer be?
So it's 0.6
What's 0.6?
mass of the rod.
Mass of the rod is 2, I think.
What? Oh yeah. I read the length.
Okay,
Yeah.
so
And so it's 10 plus 20, 30
30, what are my units?
Newton.
Okay, I think I'm going to go back up, and I'm going to write one more line, just to show what I did here. I think the sum of all of my torques should equal 0, maybe? I don't know if we actually need that, but I'm going to write it anyways. So now we've missed points last time just because we didn't have any intermediary steps. So I'm going to throw that in just in case. Okay, part C.
So the rotational inertia of a rod about its center is half 1 over 12 ml square, and calculate the rotational inertia of the rod and block. Okay. So we use parallel axis theorem.
I'll need it for part of this. Do we need that for the rod, or do we need it for the block?
For the block.
Okay,
Because we already know the center, isn't it?
I think I'm gonna need it for the rod, because we know what the inertia of the rod is about the center, but we're trying to shift it over to move it about the hinge, right?
Mm-hmm.
Okay, so if I'm shifting this center of mass over to the hinge, then I'm going to need to use the parallel axis theorem to shift over the rod, I think, the rod weight. What I'm thinking is we've got some inertia for the system, that's everything, rod block at the hinge, should equal the inertia of the rod at the hinge, system, rod plus the inertia of the block at the hinge. Does that make sense?
Yep.
Okay, then we can solve each individual part of this, and we'll just sub back in maybe. So the inertia of the rod should equal what?
1 over 12 ml square plus mr square.
What is r in our case?
Half r.
Half of, okay, but I've been labeling,
L.
okay, yeah, L over 2 squared. Okay, and we can solve that here, I guess, before we sub in. So this is the same thing as L squared over 4. So this will be 1 over 12 ml squared plus, I want this to be over 12, right now it's over 4, so this will be 3 ml squared over 12. And we can add straight across. So that's 4/12 or 1/3.
Yeah.
Okay. Then we need rotational inertia of the block. Which I don't think we need to change, actually, because it's already at the edge. So what's my rotational inertia of the block?
Of the block? It's ml squared because, yeah, L is the same.
Right.
I mean, L is full L.
Okay, then we can just sub in for the system. My inertia of the system should be my inertia of the rod. That was mRL squared over 3 plus my inertia of the block, mbl squared. So that's my inertia of the rod, mr is 2 times 0.6 squared over 3 plus my mass of the block, 0.5 times 0.6 squared. Okay, so that's going to give me 2/3 times 0.6 squared plus 0.6 squared over 2 is 0.42. And you told me the units earlier, but one more time. 0.42 what?
0.42 times 0.18. Wait, 0.6 by half. Yeah, 0.18.
Okay, so I actually already did that. So this is just 0.42 for all of this. But what are my units?
Kilogram times meter square.
Okay, kilogram times meter squared. Okay, any questions on that one?
No.
Okay, then last one. The cord that is supporting the rod is cut near the end. I want to calculate the initial angular acceleration of the rod block system about the hinge. So if we lose our tension right now, how can I figure out the rotational acceleration?
So I alpha is our torque.
That's right. Okay, so
then if there is
sum of the torque equals I alpha. Okay.
But inertia is going to be changed.
Well, our inertia will be the hinge in the block, right?
Yeah, but there is no tension, so there is only horizontal inertia.
The tension was pulling us vertically too, though, right? So I think when we cut that string, this is going to swing down. Let me fill in as much as we can first. So I've got the sum of my torques first. So what are my two torques?
M road G. No, M road.
M rod G is okay, but
M
times
L over 2.
L over 2, perfect. Plus
MB times G times L. And yeah, equals I alpha.
Okay, I'm gonna go ahead and solve for alpha first, and then we'll take a look at our inertia and see what we need to sub in. Unfortunately, I cannot cancel anything this time, but I can pull stuff out. So I'm going to factor out a g and an L from both of these terms, and then divide by the I on the other side. So that'll give me alpha is equal to GL over I times MR over 2 plus MB. Mass of the rod, mass of the block.
Yes.
Okay, make that R a little bit smaller, just so we know that's subscript. Okay. So this inertia is the inertia of the rod block system, which is what we solved for last time. So I can just sub that in.
So 10 times 0.6 times, no, divided by 0.42
Okay.
times mass of the road is 2 divided by 2 plus 0.5.
Okay, cool. So I've got six divided by 0.42 times 3/2 is 21.42.
Yeah, 21.43 maybe, or 429.
Okay, so 21.43. What are my units?
Radian per second square.
Perfect. Okay, let's throw up the scoring guide here. Okay, so we've got our diagram. Labeled tension or components, weight of the rod, weight of the block, H, force of the hinge. Okay, so that's 4 for 4 for the diagram. Then okay, tension reading on the cord. Sum of the torques is 0. Expression for torque, expression for weight and rod. Okay, we've got that down here. And then correct answer of, okay, we got 30, but we used 10, so that's okay. So that's another 4 for 4. System of inertia, rod, and block. Okay, we did that, so that's good. Parallel axis theorem for the rod, we did that. Hanging block, we did that, so that's 3 points. 3 for 3. Okay, torque equals IA, we did that. Summation. Okay, that is what we got, yes. And then 21 radians per second. Correct units on all answers. Radians per second squared, kilogram meters squared. That's good, that's good. And then last one. Torque in newtons. That's good, okay. So I think we get full credit for that. 15 out of 15.
Yay.
Awesome. Any questions on anything from today?
No, but I think I have to review for rotational inertia. It's kinda hard.
Yeah, the torque's the hardest part for me too, I think, on the test. So let me send you the PowerPoint with all the notes. That way if you want to review, you'll have it.